Hello, in this video I'm going to continue our journey towards understanding how stars work by looking at stellar classification. So to recap where we've got to, we started by looking at a basic structure of a star, going from the center with the core where the nuclear fusion's going on, then out to the radiative zone where you've got photons slowly making their way out of the star towards the surface, then to the convective zone where you've got bulk movement of matter of the star up to the surface, the photosphere, where the photons can then escape. And then, of course, beyond the photosphere, you've got the atmosphere of the star, things like the chromosphere and the corona. So we looked at that structure. Then we went on to look at diffraction gratings and how we can use them to create stellar spectra. So that's where we've got the variation of intensity of starlight by wavelength. So we're splitting out the starlight according to wavelength, and then we were seeing various features that we could pull out about the star in these spectra. So we had a continuous spectrum, which might look something like this, where this peak in the continuous spectrum was telling us something about the temperature of the star. And then imposed upon this continuous spectrum, we had spectral lines. And these spectral lines were either absorption lines, which are dark lines going downwards, or emission lines, which are bright lines going upwards. So we've got absorption lines and emission lines. So this is how we were pulling these stellar spectra together. And then in the past, I mean, people created loads of these spectra, started comparing them, and noticed that there were various common features. And they grouped stars together according to these common features, particularly the spectral lines. And this then tells us a lot about which stars are similar. And then within those stars, it tells us about the composition and the ionization state of the material in the star. And that's telling us about the temperature of the photosphere as well, as I've already said. So the reason we know that we can find out stuff about the composition and the ionization state is, as I said in the previous video, the wavelength of these lines corresponds to energy differences between energy levels in particular atoms. So we've got that relationship between the energy of a photon and the wavelength of the photon, and then that energy is directly related to a transition of an electron between two energy levels in an atom. So the wavelength that we're seeing these lines tells us what sort of elements we've got, and also just the occurrence of these lines as well tells us about the ionization state. Even at a basic level, just having these lines means that the atoms can't be fully ionized. Otherwise, you wouldn't have any electrons doing these transitions. So we need to have electrons going up and down between these energy levels. It can't just be a permanent state of dissociation between the two of them. And the extent to which we've got electrons moving around inside the atoms and how many of these transitions are happening and in what order, and the different relative occurrences of all of these transitions are telling us, if you can really get into the analysis of it all, is telling us about the ionization state. So there's a lot of information packed into these stellar spectra. Then it came, of course, to, well, how are we going to then classify these stars? It's all well and good saying we've got all of these patterns and we can see that we've got similar looking spectra. We need some way of grouping them together and saying which one's which. We want a classification system. Now, the first classification system that people were really coming up with is they were looking at absorption lines associated with hydrogen, because, of course, they're going to be a prominent feature in stars. Stars are mostly made of hydrogen. You're going to get a whole load of hydrogen lines in your stellar spectra. So they started classifying on these, and they looked at hydrogen absorption lines. And they said, okay, if we're looking at hydrogen absorption lines, let's say for the ones that have got really strong hydrogen absorption, we'll call those A, then we'll go B, C, and as they weaken, we'll just keep going down the alphabet. So you got this lettering system, which went down to about O, I think, and then they kind of ran out of the need to keep adding more letters on. So this is weakening hydrogen absorption lines. But then when people found out more and more about stars, I mean, this isn't the best way to arrange things. You know, in terms of how stars behave, is much more driven by temperature and size. These are the things that we care about. So we care about mass, temperature, luminosity, these sort of things. So let's rearrange our classification system to start. Let's take temperature then. So we're going to go hot to cold. So that's one thing we want to look at. We also want to look at our size, really, something to do with it's going to link in with luminosity along with temperature. But let's talk about size. So we're going to go from big to small. So I shouldn't have put size there. Let's just say large to small. So we've got two scales there. Because the combination of these, if we remember about our luminosity in Stefan's law, we got 4 pi r squared, Stefan-Boltzmann constant, times t to the 4. So if we want to talk about the luminosity, this is going to depend upon size and temperature. So 2 good scales to have. I mean, you know, this is what we're looking at here. So how are we going to divide things up from hot to cold? And when we're talking about hot to cold, I mean, this is very much cold in inverted commas. So this is cold for a star. But at the hot end, you're looking at things that are greater than, say, 35,000 Kelvin. And at the cold end, you're getting down to maybe 2,000 Kelvin. So that's our hot to cold. And then large to small, we're talking about supergiants going down to then dwarfs. I mean, you can have sub-dwarfs and brown dwarfs and, you know, various types of dwarf, but let's not overcomplicate this at the moment. So we've got these 2 scales. Let's look at the temperature one then. So they reuse these letters, these ABC things that they'd already started assigning to stars, and then reused them in the hot to cold bit. And they chucked out a whole load of letters, and they ended up with O, B, A, F, G, K, M. They're the main 7. People tend, certainly in the past, they used to remember this sequence with the mnemonic of "Oh, be a fine girl, kiss me." I mean, it's a nice one because it gives you the first 3 letters straight away with O, B, A. This has kind of fallen out of favour because of the girl kiss me bit at the end. So that has been dropped, although it's the one that people still remember, but it's been discouraged to be used. So other systems have been, dreamt up. People have got other ways of remembering these things, none of which are anywhere near as memorable, except the one that I came up with at university, I think, although I never hear anyone else using it, which is one big apple flattens giant killer monkey. And I like it because it splits it up into 3 bits. You've got one big apple, then what that's doing, it flattens a giant killer monkey. So it's splitting it in a 3-1-3, which I think is quite nice for the 7 words. So that's my contribution to science, probably more than anything else. And if that can catch on, I can die a happy man. So just to remind you on that, one big apple flattens giant killer monkey. Right, anyway, let's move on from that on to, so we've got those letters, they then subdivide them with numbers. So you go from 0 to 9 inside each one. So for B, say, you'll have a B0, which is the hot end of B, down to B9, which is the cool end, almost dropping into A, because the next thing along from a B9 is an A0. So you've got this 0 to 9 inside each one of these letters as well. So that is our temperature classification, our spectral class there. Then inside the size bit, we're going for supergiants down to dwarfs. We're using a Roman numeral, which is going 1, 2, 3, 4, 5. Now, again, it does go down. Sometimes you'll see 6s and 7s. Sometimes you'll see after that, use a D to talk about the dwarfs. Yeah, because actually I shouldn't have put the 5 as close to dwarfs as that, because the 5s are not dwarfs. The D's are dwarves, sometimes 6s are dwarves, 5s are not. So 5s are your supergiants. 2s are, they're bright giants. You know, they're bigger than a giant. A 3 is a giant. So a 2 is somewhere between a giant and a supergiant. It's like a big giant. The 4s are subgiants, and then 5s are main sequence. So MS. So this is main sequence. We haven't got on to main sequence yet, because that is referring to a part of the Hertzsprung-Russell diagram, and that's what I'm covering in the next video. These are the most common stars, main sequence ones. They're fairly nondescript. They're things like the sun. They're just going about their regular part of their life cycle, doing just regular stuff. And I'll talk about that more when we're looking at the life cycle of stars. So you can see with this, if you take a star like the sun, which is pretty regular, I've got this temperature scale here. We've already said in previous videos, photosphere of the sun, about 5,700 Kelvin, 5,800 Kelvin, something like that. So you can see, looking at this temperature scale, we're going to be to right of center here. And lo and behold, we are. The sun is a G. It's actually a G2V. So that is, or a G25. So that is G2 giving us the temperature. It's the hotter end of G. I mean, it's not pushing for F, but it's certainly not near K. And then we've got 5 here, the Roman numeral telling us that it's main sequence. So it's not particularly big. We're not getting anywhere near to the supergiants or even the giants or even the subgiants. It's just a main sequence, fairly regular star. So let's look at another couple of stars then for comparison. So Betelgeuse, which I've been talking about loads. Betelgeuse is, so this is a huge star, but it's not very hot. So it's an M1 and then the Roman numeral 1 at the end. So it's an M1. This is the hot end of M, but M, of course, is at the cold end of our temperature scale here. So it is not a hot star, but it is enormous. It is a supergiant. So that's why it's so bright in the sky, because we've got this huge R squared in our luminosity equation. But it's not getting a lot from our T to the 4 because it's cool. It's not like to take another star, Rigel, in the same constellation. So this is also in Orion. So where you've got Orion's belt, you've got the arms going up. Betelgeuse is up here at the top, and then the 2 legs coming down. Rigel's down at one of the feet. And now that's another supergiant, but it's a hot one. This is a B8, but we've also got the Roman numeral, the I at the end. So it's a supergiant again, but it's a B8. So it's at the hot end of our temperature scale. So that's a real powerhouse star, Rigel is. It's got this huge luminosity because of the high temperature and the large radius. It's got everything going for it. So, we can still see it's something like the 7th or 8th brightest star in the sky, but it's going to be comparatively a long way away because it's got such a high luminosity that if it was close by and it was a relatively near star, then it would be a lot brighter in the sky because it's so hot and so large. So there's a lot of variation on this, but it's not just as simple as, okay, well, let's look at all of these stellar spectra and then see which ones look the same and, oh, well, they must be the same type of star. You get variations on all of this, and you also have the problem that you don't get to see the whole spectrum. Particularly for the hot stars, if you've got something doing like, this sort of profile, and this is our visible part of the spectrum, well, all of this bit is blocked out by the Earth's atmosphere, anything UV and shorter in wavelength, so you don't get to see it in the spectrum. You're having to try and deduce things from the tail end of a spectrum, and it can end up making stars that are very different appear similar to each other, unless you know how far away they are, so you can calibrate the level of the intensity. If you've got 2 stars that look quite similar in the visible part of the spectrum, well, and you're looking at area under the curve, well, that area under the curve is going to depend on how far away the star is. How many photons we're receiving depends upon distance. So if you don't have a distance calibration, it can be very, very difficult to tell the difference between a really hot star in terms of its spectrum, like a Rigel, or maybe a white dwarf. I mean, in extreme cases, you get these things called Wolf-Rayet stars. They are really at the super hot end. These are be your O stars. really at the hot end, and they're so powerful. They've got such high luminosity that they're more or less blowing themselves apart. So you get a lot of the information we don't see in the spectrum because we can't get to that part of the stellar spectrum. And it's also blowing itself apart that you're getting to actually see the core of the star. So you start seeing spectral lines associated with heavy elements. You'll start seeing oxygen and nitrogen and things like that in the spectral lines. Now that can look very similar to a white dwarf. Now, a white dwarf is it's essentially a dead star that's been left over. You're just looking at the core of the star. The outside has been sort of puffed off into a planetary nebula or something like that. So the outer part of the star has been stripped away, and you're looking at the core, which is still releasing residual energy. It's not fusing anymore, but it's releasing the energy that is already created. But because you're looking at the core, you're looking at heavier elements. And it's very hot because it's a core, and you're seeing oxygen and nitrogen and things like that in the core. So the spectra can look very similar for a huge star and a really small star. Let's take an example of a white dwarf. So say Sirius B. So Sirius, the brightest star in the sky, at least apparently, when we look at it, it looks brightest in the sky because it's very close to us, Sirius. And Sirius is a binary star. You've got two stars there. You've got Sirius A, which is the main star, and then you've got Sirius B, which is a white dwarf in that binary system. Sirius B is an A2, so it's really hot. It's at the hot end of A, and it's a dwarf. So sometimes you see it written DA2, sometimes you'll see it A2D, sometimes you'll see an A2 with maybe a 6, or I've written a 7, a 6 at the end. So there's variations on how the stellar classification is written out. But you can see that, okay, Sirius B, it's a small star, it's a white dwarf, but it's an A. So we need these D classifications are particularly important. And it can be hard to tell them apart. You can look at a new star and think, well, what is this? Just based on this little bit of information I've got here, I know it's hot. But what is it? Is it a star? Is it a white dwarf? Is it a Wolf-Rayet star? Who knows? I mean, it could be huge, it could be small. So it's still not easy to classify these stars. Trying to think if there's anything more I want to say about this. Yeah, in terms of colour, okay, the sun is referred to as a yellow star. And sometimes you'll see these colours match to the temperature scale. So hot being blue, down to cold being red. The sun is yellow. I mean, in blue to red, so G fits with the rainbow that we're going to have yellow in the middle. So that doesn't mean to say if you're going to look at a G star, a G class star that is going to look yellow through the eyepiece, it will still look white. It just happens to be where the peak of the spectrum is yellow. But you've got so much coming from all of these colours in the spectrum really for a G-type star that it's not going to look bright yellow. It's just going to look regular star-like. So they don't have these massive, it's not like we're saying, oh yeah, we've got this big yellow peak. It's nothing like that. You get these broad things with a peak in the yellow part of the spectrum. So don't get too bogged down on the colour bit. Although if you're at one end, I mean, Betelgeuse does look distinctively red. If you've got really something going off to one end of the colour spectrum in the rainbow. So that's on colour. Also in terms of how many of these stars there are around. I mean, there are a lot more of the cooler stars than there are the hotter stars. So you're going to get a lot of G-type stars and K-type stars. There's just loads of them around. You've got more main sequence stars. So these sort of classifications that you're seeing from the sun, there are just loads and loads and loads of those. If you did a survey of the stars in the Milky Way, you went around the whole galaxy, you'd get more stars at this end. The thing that confuses people with it and makes them think that isn't necessarily going to be the case when they start out in this is when you observe stars, you go out and you do an observing session, there are loads of B and particularly A type stars in the sky. And And it's because they're brighter, so you're more likely to be able to see them. So you've got this trade-off when you're actually looking at stars in the sky. You've got, well, how many of them are there? And there's more stars as you move down to the cooler end. But they need to be bright enough to be able to actually see them. And A is kind of the the peak of that trade-off. It's the middle ground where A-type stars, there's enough of them that there can be a lot of them in the sky, and they're bright enough that you can see them far away. If we're going to be looking at G-type stars and K-type stars, they need to be relatively close so we can see them at all. So there is a bias to the A and B types for the stars that you can see in the sky. So don't think just because you're looking at all of the constellations and like, oh wow, it's another A-type star, it's another B-type star, that means that the galaxy is just filled with A and B stars, because that isn't really how things work. Right, so that's the stellar classification system. The name of this system is the Morgan-Keenan system. So Morgan-Keenan system. And you just see this all over the place with stars. Every time you look up a star, it will give you this classification of these letters and numbers. Sometimes it has little bits added on the end, but if you're interested, you can look those bits up yourself. Now that we know stellar classification, we need to come back to this idea of the main sequence and all of these different giants, which is something we're going to do in a couple of steps, because we need to unpick luminosity. So that means we need to have some way of determining how far away stars are. Because if we don't know how far away they are, we only know how bright they seem to be. We don't know how bright they actually are. So we need to solve this problem of stellar distances. And then once we've done that, we can then pull together the combination of spectral class, which is essentially a measure of temperature, and luminosity, which is then going to be a measure of temperature and size. And then we're going to see that there is a very strong relationship between luminosity and temperature of stars. That will then allow us to classify stars as different types and tell the whole story of stellar evolution. So we're nearly there. I mean, that story of stellar evolution is going to come out of the Hertzsprung-Russell diagram. And all we need now in order to be able to tell that story is unpick stellar distances, which is what I'm going to do in the next video. That's going to help us pin down luminosity, and then we can get into stellar evolution. So next up, stellar distances.